Hi, welcome to our video. In this video, we are going to introduce you to the second order linear differential equation and its application. Our group members consist of Chen Kawai, Chu Junjie, Yam Yongxian, Ho Junyong, So Wei Kai, and Teo Junlong. First of all, the second order linear differential equation can be classified into two parts, which are homogeneous differential equation and non-homogeneous differential equation. A second order homogeneous linear equation is considered as a d square y dx square plus b dy dx plus cy equal to 0. Initially, let the equation to be am square plus bm plus c equal to 0. Then, solve and get the roots of equation m. There are three conditions. Case 1, roots are real and distinct, m1 not equal to m2. Case 2, roots are real and equal, m1 equal to m2. And case 3, roots are complex conjugate numbers, m equal to alpha plus minus I beta. For case 1, we have m1 not equal to m2. The general solution is yc equal to ae to the power of m1x plus be to the power of m2x. For case 2, m is equal. The general solution is yc equal to a plus bx multiplied by e to the power of mx. For case 3, since we have complex roots, the general solution is yc equal to e to the power of alpha x multiplied by a cos beta x plus b sin beta x. Next, for the second order non-homogeneous linear differential equation, the equation is considered as a d square y dx square plus b dy dx plus cy equal to fx. The solution to the equation is given by yx equal to complementary function ycx plus particular integral ypx. The ycx is determined by the method mentioned just now, and ypx is solved by either of the two following methods: method of undetermined coefficient and method of variation of parameters. For the method of undetermined coefficient, there are four cases. Case 1, fx is a polynomial form with degree n. Ypx equal to x power of r, cn x power of n plus cn minus 1 x power of n minus 1 plus so on until c0. It's noted that r should be 0 first, then compare yp with yc. If there's any similarity, a bigger integer for r, in this case 1, will be taken until there's no similarity. Then differentiate yp with respect to x twice to get yp prime prime. Substitute yp prime prime, yp prime, and yp to the original equation to get the values of c. Case 2, fx is an exponential form, ce to the power of mx. Ypx equal to x power of r, de to the power of mx. Case 3, fx is a sine or cosine function. Ypx equal to x power of r multiplied by c cos beta x plus d sin beta x. And finally, case 4, fx is a combination of the above cases. Ypx equal to yp1x plus yp2x plus yp3x. The process of finding r are the same for every cases above. As for the cases not mentioned above, ypx will be solved using method of variation of parameters. To carry out this method, first express the given equation in the form of a d square y dx square plus b dy dx plus cy equal to fx. Second, determine the values of a and fx. Third, find the homogeneous solution yh equal to a y1 plus b y2. Fourth, calculate the Wronskian w equal to modulus y1, y2, y'1 and y'2. Fifth, calculate u equal to negative integration y2 fx over aw plus a and v equal to integration y1 fx over aw plus b. And finally, obtain the general solution using the formula y equal to uy1 plus vy2.
Now we are going to discuss on the application of second order linear differential equation. In our case, we take the motion of a mass spring oscillator as the application. A damped mass spring oscillator consists of a mass m attached to a spring fixed at one end. A general equation of its motion should take into account the forces acting on it due to the spring elasticity and damping friction. In this case, we consider there is no external force exists. Assume a mass spring oscillator having mass m, spring constant k, and damping coefficient b. When the spring is unstretched and the initial mass m is still, the system is at equilibrium. We measure the coordinate y of the mass by its displacement from the equilibrium position. When the mass m is displaced from equilibrium, the spring is stretched or compressed, and it exerts a force that resists the displacement. By applying Cope's law, it can be assumed that the force exerted by the spring is equal to negative ky. Next, our concern is move on to the frictional force experienced during the motion of the mass spring oscillator. Since frictional force is usually modeled accurately by a term proportional to velocity, and velocity can be found through first derivative of displacement y with respect to time t. Thus, the formula of frictional force is equal to negative b times with first derivative of y. By applying Newton's second law, we know that the force equals mass times acceleration, and acceleration equals to second derivative of displacement y with respect to time t. Thus, the formula obtained is F equal to ma, where it can also be m times second derivative of y. Lastly, by applying Newton's third law, an equation of these forces acting on the system is obtained, which is m times second derivative of y equal to negative k times y minus b times first derivative of y. And by shifting the variables, the equations as shown below can be obtained, which is a second-order linear differential equation. To further explain, let us take an example. When we have the mass of solid object m equal to 7 kg, spring constant k equal to 700 Newton per meter, and the damping coefficient of 1/4 or 0.25. By using the formula stated above, we can then substitute the values into the formula, which we will obtain the second equation shown here. The third equation is the characteristic equations of the second equation. By using the formula negative b plus minus square root b squared minus 4ac over 2a, where the value of a is 7, b is 0.25, and c is 700, we can then solve the values of n, or we can obtain the roots of the equation. Since the roots obtained here are complex conjugate numbers, we can conclude that the general solution y is equal to exponent with the power of negative 0.01786x multiplied with a cos 10x plus b sin 10x. In a nutshell, we can apply the methods of second-order linear differential equation to solve a problem as long as there is a dependent variable being differentiated twice with respect to a given independent variable. With this, we have come to the end of our video. We hope you can get a clear idea of the application, which is the motion of a mass spring oscillator, through our video. Thanks for watching.